We've spent some time talking about the mean function mu, the autocovariance function gamma of h, and also the autocorrelation function rho of h. Now, these quantities represent the true values, or you can think of it in a statistics context, the population values. These values will not be known in actual practice. So what we're going to need to do is take a sample so we can estimate these corresponding values. And that's what the purpose of this subsection of the notes talks about, is how do we do the estimation. Throughout here, we're going to make an assumption of weakly stationarity. Okay, so with respect to the mean function, when we have a weakly stationary time series, that means, of course, expected value of x1 is equal to mu, expected value of x2 is equal to mu, all the way up to the nth value in our time series. So, since each of these random variables have the same mean, it would make sense then, in terms of observed values, to simply take the mean of all the observed values, and that's how you get the estimate for mu. We can call it x bar. Note that how this would not make sense, though, if we didn't have the weakly stationary assumption, because what that would say is some parts of your time series have a different mu than other parts, and it wouldn't make sense then to average all the observed values in your time series to estimate then just one mean. And so with the weakly stationarity assumption, this is why we can look at an estimate that simply is the average of all the x's. Okay, now let's talk about the autocovariance function, the sample version of it. And to do this, let's think about how we would normally estimate a covariance. What you would do, let's say if you had two random variables, x and y, with their observed values, you would take each of the x's, subtract off its mean, take each of the y's, subtract off its sample mean as well, and then add these products all together, divided by 1 over n. This would be the estimated covariance, or one way to estimate the covariance between x and y. We're going to do a very similar thing here now with respect to a time series. So we're going to call our estimate gamma hat of h. So again, h is the lag. And what we're going to do is take x sub t plus h. So we're going to go h time points, you could say, into the future past t. Subtract off the corresponding mean of the series, sample mean of the series. Take that quantity times x of t minus x bar. So again, this product here then that we're going to take is very similar to what you just saw in the regular old covariance expression. We're going to sum from t equal 1 to n minus h, and we're going to take this all times 1 over n. That's our sample autocovariance function. Now, why are we going up to only n minus h versus n itself? Well, it's so that we have actual observed values. Let me get an eraser here. In the time series here. So, for example, at t equal 1, we would have x sub 1, and we also would have x sub 1 plus h. Now, when t is equal to n minus h, look what happens. We have x minus h, and then we have n minus h plus h. Those h's cancel out, and so we're at x sub n. So what that upper index then in that summation allows you to do is to make sure that you don't go beyond n observations that you have in your time series. Now, just like what we saw with gamma of h, gamma hat of h is going to be equal to gamma hat of negative h. Meaning it doesn't matter if you're going to, let's say a positive 1 lag or a negative 1 lag, you're going to get the same thing. What if h is equal to 0? So gamma hat of 0, look what that is there. Sum, let's see, t equal 1 to n now, because h is equal to 0. X sub t plus 0, which is x of t, minus x bar, times exactly the same thing again. And so what we get here is a regular old sample variance. Now the one difference from what you've seen in your very first stat course when you took a sample variance is that notice we're dividing by n here rather than n minus 1. In the end, it doesn't really matter because, in a time series context, we're typically going to have a large n. And so whether you have an n there or n minus 1, it's going to be approximately the same thing. Well, what is this quantity if h is equal to 1? Well, take a look at that yourself. What this is saying is that now we're looking at, let's say, x of 1 versus x of 2, x of 2 versus x of 3, and so on. So we're looking at a lag of 1. Okay, so we've talked about this, we've talked about that. Note that this is not an unbiased estimator of gamma of h. However, as n gets larger, the bias simply goes to 0. So that's why we're not really concerned about having at least for a finite sample, a bias estimate. So if we have the sample autocovariance function, then we would also be interested in the sample autocorrelation function. And as you might expect, all I do is I take my autocorrelation function and put hats on all the stuff that we don't know. And so that's how you get the sample autocorrelation function. So here's a question. What does rho of h equals 0? Notice I don't have a hat there. What does it mean, and why would this be important to detect? So if rho of h is equal to 0, that says that there is no linear dependence between or in your time series at that particular lag. This is a very important thing for us because let's say if I want to use, let's say, x of t minus h to predict x of t, generally speaking, at least in terms of a linear dependence context, this x of t minus h is going to have no effect on what x of t is. So it wouldn't make sense to go back to h time points in the past to predict, to forecast what you would be at x of t. So this is a very important concept to understand of, well, when is rho of h equal to 0? When is it not equal to 0? Because that controls then how you want to predict, how eventually you want to forecast with your time series. So since this is so important, then we will actually be doing hypothesis tests concerning is rho of h equal to 0 or not. To do any kind of hypothesis test, you need a corresponding statistic that's going to help estimate your unknown quantity that you have. And with the statistic, you're going to need to understand its sampling distribution. So for example, let me get a little bit more space here. In your very first stat course, you talked about, well, how can I do a hypothesis test for the population mean? Don't worry about this don't think of this as a time series. Just your very first stat course, you talked about how to do a hypothesis test for the population mean. And to make things simple here, let's assume that the population mean that we're interested in, is it equal to 0 or not? And so there's a few different ways to go about doing this, but all of them concern, let's say, your sample mean. Let's think of y bar as a random variable. Now we know from the central limit theorem that y bar has an approximate, so I'm going to put a tilde with a dot on it to mean approximate distribution that is a normal distribution with mean under the null hypothesis, mean equal to 0 and variance of sigma squared divided by n. One could form a test statistic such as this. Let's call it z is equal to y bar minus 0, the hypothesized value of mu, because in hypothesis testing we always assume that the null hypothesis is true to begin with, and we take that divided by sigma divided by the square root of n. under the null hypothesis, as this has an approximate standard normal distribution. So what we do is we look, is y bar minus 0 over sigma divided by square root of n, is that greater than, let's say, the 1 minus alpha divided by 2 quantile from a standard normal? Is this quantity instead maybe less than the 1 minus alpha divided by 2 quantile from a standard normal? Now this phrase here, quantile from the standard normal, let's make sure that you understand that. So if alpha was 0.05, this would mean that this z with a subscript 1 minus alpha divided by 2 would be a positive 1.96. Okay? So if this test statistic is either greater than this quantity or less than the negative version of that quantity, that says then there's sufficient evidence to indicate that there's evidence against the null hypothesis, meaning that mu does not equal 0. Now, another way to look at this, though, is, let me get my pen back out. Oh, I'm sorry, my eraser, I mean. What I could do instead of having the denominator sigma divided by square root of n, what I could do is simply multiply this quantity by sigma divided by square root of n, sigma divided by square root of n, and now I can check the sample mean itself. Is that sample mean greater than this quantity or less than that quantity? If so, then I could reject the null hypothesis. When you first learn about hypothesis testing, often you don't think of it that way, but this is mathematically an equivalent way to think about it. We're going to be then using that very shortly, that concept, to do a hypothesis test for rho of H. Okay, so y bar has a particular sampling distribution to it. This is from the central limit theorem. You could also work with a t distribution as well. I just did it here with respect to the standard normal. Now, the sampling distribution for rho hat of H, so the estimate of rho of H, is as follows. If rho of H is equal to 0, x of t is stationary, and the sample size is large, of course, then the central limit theorem was with respect to the sample size being large too, then rho hat of H has an approximate normal distribution with mean 0 and a standard deviation of 1 divided by the square root of n, or the standard deviation just symbolically I denote as sigma of rho hat of H to help us know, well, which standard deviation am I talking about. So in other words, what this is saying is that rho hat of H has an approximate normal distribution with mean 0, variance of 1 over square root of n. This is for a large sample, stationarity, and rho of H is equal to 0. Now, a proof of this sampling distribution relies on having a PhD level asymptotics course. In that kind of a course, if you talked about this particular result, sometimes you do, sometimes you don't. You would write it something like this: the square root of n of rho hat of H minus 0 converges in distribution to a normal random variable with mean 0 and variance of 1. I just put that there because sometimes some time series textbooks will go to this formality of talking about convergence and distribution, and basically what this just means is what I had written in a more simplified form up there. Okay, so now that we have the sampling distribution, then we can use it for hypothesis testing, just like what I did originally with that sample mean. So what we're going to do is this. We're going to check, is this rho hat of H, is it within the bounds of plus or minus the 1 minus alpha divided by 2 quantile from the standard normal divided by the square root of n? If it is, we say don't reject HO, where HO is, here's HA, we have not equal. If, however, rho hat of H is outside of this, you could say, interval, then we would reject the null hypothesis. And that says we have a significant autocorrelation, or probably a better way to say is that yes, we do have evidence that rho of H does not equal 0. Okay. Excuse me. So let's take a look at an example. We're going to go back kind of to an example that we've seen before with an AR1, an autoregressive 1 model with a sample size of 100. Now in this particular case, we're actually going to be working with some data that I've simulated in the past. So it's not going to be exactly the same data that we had saw previously when we used a for loop to come up with it. The actual data itself is stored in an plain ASCII text file. This is what it looks like here. The columns are space delimited, so we'll have to take that into account when we actually read in the data. Notice the very first row of the file itself contains then the actual variable names. So I have T for time and X for the actual data itself. So let me go over here to 10 so I can read it in. Since this is a plain ASCII text file with space delimitation, I'm going to use the general function read.table to actually read in the data. Here's my file. Header equal true, corresponding to the first row of the data, has the variable names. And it is space delimited, so I use the SEP argument and put equal quote quote to mean space delimited. If I really wanted to, I could put an extra space there too to emphasize that. I'm going to put that into an object called AR1. Take a look at the first 6 observations of AR1, compare it to what was originally in my file itself, and then I'm going to pull X out of AR1 and put it into an object X, just because I wanted to do that since we're dealing with X here as our variable of interest. So here's then the corresponding data as seen there. And indeed, this does match up with what was in the original file. Then using methods that we've seen previously, we can do a plot of our corresponding data as well. So here's a plot of the AR1 data. Just from looking at this plot, it looks like we do have some dependence between the different values there. We see some trends as we go along here in the plot in terms of we keep on going up, for example. Now let's actually quantify that dependence that we see in the sample itself through calculating these autocorrelations. So the way that we can do that in R is to use the ACF function, where the first argument is called X, and that's where we put in where our data is, which happens to be called exactly the same thing, X. We tell the ACF what do we want to calculate. We want to calculate correlation. We put a nice title on the plot as well. And with this function itself, it's going to calculate the autocorrelations and put them into this object row.x, but it's also going to be generating a plot of these autocorrelations as well. So let me go ahead and do that. So my plot opened up in a different monitor than what I'm using right now. And here we go. So here's the autocorrelation plot. And so that I can nicely or easily write on this, let me jump back over here to Word, and here's exactly the same plot. And so what we see here is that at lag 1, the autocorrelation, rho hat of H, is approximately, is approximately equal to is equal to 0.674. So that should be a 1 there. Relative to the y-axis here. So the y-axis gives us, sorry, should have started with that there, rho hat of H, and the x-axis is the lag or H. So here is then rho hat of 2, and so on. So we can see now, actually by default, that the ACF function actually goes up to lag 20. If you want to change that to a higher number or smaller number, you can use the argument lag.max and specify something other than 20 inside the function itself. Also, we see something that's kind of annoying, and that is, notice it actually gives you at lag 0 what the autocorrelation is. Well, it's 1. And in fact, it will be 1 for any data set, because what this is saying is, what's the correlation between x of t and x of t? Or like x1 and x1, x2 and x2, and so on. Of course, they're exactly the same, so the autocorrelation will be +1 always. Ideally, it would be nice if we didn't have that on the plot. I'll talk about how to do that shortly. Now, also here you see some dashed blue lines. Excuse me. What that corresponds to is this hypothesis test that I just mentioned, in terms of if an autocorrelation is outside these blue lines, which are drawn at, by default, plus or minus 1.96 divided by the square root of n. If an autocorrelation is outside that, then it says, yes, there's sufficient evidence to indicate that the true autocorrelation does not equal 0. So what we see here at lag 1 and lag 2, we do have sufficient evidence to indicate that. So we do have some dependence there for lag 1, lag 2. Of course, you got to ignore, though, at lag 0, it doesn't make sense to look at that particular value there. Okay. Now notice we have a 1.96 here, and this is a 0.025 quantile from the standard normal. If you wanted to change that to something else, you could use the CI argument in the ACF function to do that. Okay, so what I can do in my command prompt, I can type row.x, that's where I say the results from the ACF function, and you can see here are the corresponding estimated autocorrelations corresponding to a particular lag. Row.x itself is actually a list in terms of R's terminology of how it's storing information. So row.x, if I pull out ACF from that, this is where how I can get my actual excuse me. This is how I can get my actual autocorrelations out. One thing you got to be careful about is that notice the first row corresponds to row hat of 0. The second row corresponds to row hat of 1, and so you can see the row number is essentially 1 greater than what your actual lag is. So some questions then, well, what's happening to the autocorrelations over time? Well, let's take a look at the plot. We can see that we start off with some rather large autocorrelations. We have sufficient evidence that the true autocorrelations are not equal to 0. But then as we go along through time, we see essentially all these autocorrelations are within those blue dashed lines. So we don't have sufficient evidence to indicate that these autocorrelations are different from 0. Well, why? Well, let's just think about this in terms of our model here. So again, this is data simulated from an AR1. This is what the model looks like. And so, it makes sense for lag 1 for there to be some strong or large positive autocorrelation. Because notice inside this model, if I go back one time point, that's going to have a really important effect about what x of t is. Well, what about now a lag of 2? Well, again, I could plug in, and we've seen this before, I can plug in what x of t minus 1 is. It's 0.7 times x of t minus 2 plus wt minus 1. And again, this makes some sense that when I'm 2 lags off from x of t itself, that I do have some positive dependence. But it also makes sense that this positive dependence should be less, because notice I have a 0.7 here, I have a 0.7 there, so now I'm down to 0.49. And so it makes sense to have less of an effect, that this x of t minus 2 is not going to affect x of t as much. And one could go ahead and plug in, well, what is x of t minus 2 as well? Or x of t minus 3, and so on. Or let me back up a second here. You could plug in, well, what is x of t minus 1? Well, it's 0.7 times x of t minus 3 plus wt minus 2. And with that 0.7 there, now I'm going to have out in front 0.7 cubed. And you can see now, when you go down to 3 lags, while it will have some effect, it's going to have a lot less of an effect than what you were at lag 2 or lag 1. And so that's what we're seeing here in this plot then for this sample, that we're a little bit close to the borderline there. That as you go along, typically you're going to have less of an effect. Now you might be wondering, what about right here? Well, because that's close to the borderline. This is not something necessary to be worried about. Remember, we're doing essentially 20 different hypothesis tests here. There's going to be some sampling variability as well. What you're really looking at is something that's, far above that or far below that dashed blue line. We'll be continuing to look at these kinds of plots throughout the course, so we'll be seeing more examples of this too. Okay, let's get back to where we were. So is there positive or negative correlation? Well, there's positive correlation. And again, it makes sense for what that coefficient is on that x of t minus 1. And we've already answered that particular question as well. Okay, so similar to what I mentioned before, R plots rho hat of 0 equal to 1 by default. It would be nice if R did not do that, but unfortunately it does. If one wanted to remove that from the plot, here's one way to do this. Okay, let me come back up here. Let me actually do a little bit of erasing as well to clear things up. Okay. Now notice the first autocorrelation that could be plotted, at least with respect to R's calculations, is at lag 0. But if you notice here, we have a little bit of extra space here between 0 and that y-axis where it's drawn, that y-axis. Well, why is that? Well, by default, in the graphics package for R extends this out 4% more than where your minimum is on the x-axis. The same thing happens over here. It extends it out 4% more as well, relative to the entire plot. So to tell R, hey, don't extend it out at all, what I can do is use the par function, similar to what we've seen before, and say for my x-axis, use the argument I here. And what I corresponds to is simply remove that default 4% extra space. Okay? Then, also, inside my xlim argument, I can say let's draw from a minimum of 0 up to 30 for that x-axis. And then if you ever wanted to go back to having your x-axis drawn in a regular manner, you can then use that par function again and use the R function for a regular manner. And so this is what then the plot looks like. And so while we still see lag 0 there, what happens is R is actually drawing a line right on top of where how that y-axis is drawn. And so in the end, you really don't see it, or you can't differentiate it from the y-axis, the line there. And so this is one way that you can get around this issue. And you might think, well, this is a minor issue. Why are you taking 5 minutes to do this? The reason being is because we're going to be looking at a lot of ACF plots of data. And I've seen this happen, and I've done it myself as well. I've seen it happen with students. Is that you see this right here. It's like, wow, I have a significant autocorrelation. I'm not even paying attention to what that lag is. And so you think, okay, I have 1, I have 2, I have 3 autocorrelations. And since you have 3 autocorrelations that are, let's say, significant, then you're thinking, okay, that's going to lead me to use a particular time series model. That's incorrect. You should only be looking at lag 1 and lag 2 instead. So you only have 2 significant ones. You'll see that as we go along and try to choose ARIMA models for our data, how one can make that mistake. Okay. Well, let's say that you want the autocovariances for some reason. How can you do that? Well, simply, instead of having type equal correlation, put type equal covariance. And here's what the autocovariance looks like. Of course, it's going to be the same shape. Now, to help understand what these autocorrelations are measuring, how about we simply look at Pearson correlation coefficients for, let's say, a variable x of t, and then we shift everything down 1 time point, shift everything down 2 time points, and shift everything down 3 time points. So in other words, you can think of this as, outside of a time series class, we have 4 different variables that we're working with. And we want to find the regular old Pearson correlation between them. So for example, let me actually come back over here. So here's my data again. Let me actually copy and paste some of this. Excuse me. Let me format this nicely. It's not going to be nice, but I think we'll get the point here. So x1 is 0.0417, x2 is 0.37, x3 is negative 0.185. And so what I would like to do is actually set up a new data set to work with so that I can look at one variable, my original variable itself, and then my next column in my data set is going to have everything shifted down 1 time period. The next column, 2 time periods. The next column, 3 time periods. And then find the Pearson correlation coefficient between each of the columns. And so the way that we can do that then, let me remove that, is first of all, I'm going to come back to this function that we've seen briefly once before, the TS function. And I can use the TS function to specify to R that indeed I do have a time series. Sometimes this is useful, sometimes obviously with that ACF plot we didn't really need to do that. But here I'm going to actually do that myself, and let me just show you again what the effect is. Now R attaches some additional information to your data. It says it's a time series. It starts at time 1, ends at time period 100, and a frequency of 1. So it's like maybe I have yearly data. So here is, for example, x1. Then what I'm going to do is as follows. I'm going to take the function ts.intersect, which is going to help me form these 4 columns of data and actually line them up all properly. Where I'm going to take the x.ts that I just formed, and then I'm going to go down 1 time period and form x.ts1, and what it's going to be equal to is the following. I'm going to use a function called lag to basically shift everything down 1 time period. So k corresponds to how I'm shifting it down 1 time period. So let me actually execute that segment of code so you can see it. Now, it says the series starts at time 2 and ends at 101. You might be thinking, well, wait a second here. You said you're shifting down 1 time period. You'll see why I said that shortly. Then I'm going to do for 2 time periods, and then for 3 time periods. Let me go ahead and put that all into set 1. We'll do a head of set 1. And this is what we get. So let's see here. get everything on a nice, there we go. So notice here, for x.ts3, that was my original x1. 0.3719 was my original x2, and you can see my original x3 and my original x4. Now notice how everything is nicely lined up here. Basically, I'm going to start at time point 4, and I'm going to put in the exact same row, time point 3, time point 2, time point 1. So that's why you saw me use a negative k value. So that here's x4, x3, x2, x1. Now I have here x5, x4, x3, x2. Everything's nicely lined up. Let me jump back over here to Word. And so if we looked at set 1 itself, the entire time series, you can see that it starts at time point 4. There's x of 4. Now in R, I can use the core function to find then the estimated correlations between these variables. If you're familiar with a correlation matrix, that's what it actually finds. So between my current time point and one time point in the past, I have an estimated correlation of 0.689. Go to 2 time points, 0.406. 3 time points, 0.17. Notice how this is almost exactly the same as what we had when we were calculating these autocorrelations here. So what I have just highlighted right now, compare that to what I was highlighting before. Because it's approximately about the same formula for what you would have with a Pearson correlation. Then we can do a scatter plot matrix as well with these 4 columns of information. There's a variety of different ways to do a scatter plot matrix in R. I'm choosing the scatter plot matrix function that exists in the CAR package. This is a user contributed package that you need to download and install. And to use the scatter plot matrix function, I can use the formula argument where I say formula equal and then tilde the actual variables of interest, in other words, my columns of my data. And then I have a few different other options there to make it look nice, and this is what we get. And so this particular plot here corresponds to the correlation between xt and xt. I don't know why my computer is doing this. Xt and xt minus 1. This plot corresponds to give me a visualization of the correlation between xt and xt minus 2, and so on. And so that we can see that as that lag increases, then my association gets weaker, meaning the points are farther from each other and becoming more and more like a random scattering. Okay. So some comments here. So we've talked about the TS function, the lag function. Yeah, I think we've talked about all these here. So my last example is, well, let's go back to that OSU enrollment data that we talked about previously. Take a look at the autocorrelations associated with that and try to make sense of why what we see, why that occurs. So I take my enrollment out of my OSU.enroll data frame that was used to actually, that contained the original data read in. I put it into an object called X. I use my ACF function. I print off then my corresponding estimated or sample autocorrelations. And then eventually I get to a plot here of them. Okay. Note that this first one here is at lag 0, so let's ignore that. So here's lag 1, lag 2, and lag 3. Now remember, with our data, we have fall, spring, and summer enrollments. And these essentially repeat every year. And so what this is looking at right here, notice I have a decent sized negative correlation. And what this is telling me is that if I look at a lag 1 difference, in other words, let's say compare fall to spring, or spring to summer, or summer to fall, I have a negative dependence there. That should make some sense because we know like fall is the highest, and then we go down a little bit for spring. So high numbers correspond to low numbers now for spring. Similarly, we have the same thing happening for spring to summer, and then summer to fall I have the opposite, but still small corresponds to large. That's why I have a negative correlation for lag 1 separation. A similar thing happens for lag 2, but take a look at what happens for lag 3. Look how large that is. Well, why? What this is basically saying is as follows. Let's compare fall 1989 enrollment to fall 1990, to fall 1991, to fall 1992. And if you go back to the original plotting the data, you can see that we have high values, or we have similar values, I should say. That's a better way to put it. We always have similar values for those corresponding falls. Also at lag 3, what this says is do the same thing for, let's say, spring 1990, spring 1991, spring 1992, and so on, where we're looking at every 3 time points in the time series. We have very similar values, and that's why we have this strong autocorrelation there. Seeing something like this, and notice how that pattern repeats itself. Now I'm at lag 6, so that would be like comparing fall 1989 to fall 1991, because it's a 6 lag difference there. We see the same constant thing happening there, and that's actually going to be a very important thing for us to detect. To foreshadow some stuff that we're going to see is that when I see something like this, this tells me I have non-stationarity in my time series, and we will want to deal with that so I can get a stationary time series. More on that later in the course. Okay, so just some notes. We've talked about this pattern, and we've essentially talked about some other stuff that's going on here. So with that, then, that's a way this subsection gives you some information about how, with an actual data set itself, we can start estimating some of these true dependencies that we have in our data. We can also estimate then the corresponding mean of the time series as well.